Hi everyone. Just to fulfill your request that we do some revision on the uh, topic that include in the second test. Alright, for this about half an hour I will talk on chapter 4, particularly in subtopic direction and derivative and the equation of tangent plane. Equation of a tangent plane to the surface. So so I'll not go as detailed as in the notes or in the previous video, but I'll give you the basic idea what we are looking for that when we try to find the direction and derivative, as well as when we try to find the equation of a plane. Alright, so first thing, now let's call this video number, I forgot what number is this, 32 or 33, cannot remember. Let's say 32. Can't really remember. Revision, I call it revision 1. If I have a time, I will do the revision 2, which is that I include chapter 3 only. For this, I will just focus on chapter 4. I have about half an hour. Alright, first directional derivative. Directional derivative. Now, what is directional derivative? The purpose is to find the rate of change. Okay, the purpose is to find the rate of change. Okay, to find the rate of change of a function, given function, I would say, of a given function. That my f of the form like f(x,y,z) or f(x,y) only, or f(x,y,z) in a particular direction. Okay, given a function, basically in any direction, as long as you are given which direction, we can find the direction. Okay, so I would say that in a particular direction, and of course we need a point, right? Okay, so for the theoretical aspect, you can look at our notes. You can find which video it is, I cannot remember. So basically what we do in terms of notation, we write like this: d as a differentiation in the direction of u, our function f x y z. Okay, this is given as del f dot u. So if you look at this definition of directional derivative in the direction of u for the function f, okay, so we have dot product here, which means the output must be scalar. You cannot have a vector. Just look at this: you have a function here you have a vector, here you have a vector, so you have that dot product there, so it should be a scalar. And remember that del, we define del is del x, del x, del y, del z. Okay, so I think that's what we need. I give you example. Let's say okay, give you example. Let's say we have a function f x y given as x squared y cubed 4y. Okay, and and a vector v, we have 2, 5, at point 2 minus 1. Okay, let's say we have this. Okay, so what do we need? We need, look at the formula. We need del f, we need u. U is a unit vector. So if you don't have a unit vector, you have to find out what is the unit vector. Now we want to find, okay, we want to find the directional derivative of function f in the direction of v. Here in this case v, this is not a unit vector, so you need to write, or you need to find the unit vector in the direction of v at this particular point. Okay, let's give a name. Let's call this point P. So just to make us easier to write. Okay, so we need that del f. So find out what is del f. Okay, del f, this means we have del x, del y, del z of f. So which means we differentiate respect to x, y, and z. Alright, so we have del x, what we have 2x y cube. That one we don't have. Del y we have 3x squared y squared minus 4 del z. So in this case we don't have z because our function only two-dimensional or two variable function, so just that. Okay, then what else? We need u. Alright, what is u? We were given v, not u, but we can find u. U is a unit vector. This is v over magnitude of v, which is magnitude of v. What is it? So we have 1 over square roots 4 plus 25, correct? Because 2 squared 4, 5 squared you got 25, and then v you have 2, 5. So this is unit vector. This is unit vector. Unit vector. Okay, and at point P, when are you going to use these points? You're going to evaluate the del f at that particular point. Okay, evaluate that at that particular point. So what does it mean? So it means that we evaluate those del f at P. Okay, that gives us what? So we have 2xy cubed, x is 2, y is negative 1. So you substitute that. So we have 2, x is 2, y is negative 1 cubed. Alright, 3, x is 2 squared, y, you have y is minus 1, oh, minus 1 squared, minus 4. Okay, so simplify that. So you have what is, this is negative, so negative 4 there. That one you have a positive, so 4 times 3, 12, minus 4, 8. Negative, 8, right? Please check the calculation. Alright, so therefore, you can find d u f, okay, directional derivative at for function f in the direction of u, given as del f dot u at point P, of course at P. So this is just minus 4 8 dot those things 1 over sec 29 2 and 5. You can solve this whatever it is, should have no problem. Okay, so it's simple. What you need to do is find the del f, find the unit vector. That's it. Okay, and then another thing you need to know is that how to find how to estimate the rate of change of f in a certain direction. Okay, how to find the rate of change of f in a certain direction. So, okay, what is rate of change? What is rate of change? Rate of change. What is this? Okay, I give you a simple example. Let's say we have this function. whatever function it is, but let's say the function look like that. So what we mean by rate of change is that when x move from a certain point to another point, we have small move in x. Let's say del x. I would say, let's say this is x. Let's say this is x plus h. So h is very small. So if you want to find del x, so which means we have x plus h minus x that you have h. This is example, yeah? This is example. So which means the difference or the change in x is h. Okay, the change. So if you were given the change of x, you were given this much, then what we want to find is how much the change in y. That. Okay? So it's about this thing. Then this del x, this del y, we can always change that in terms of times. Then what happened to the given function? Yeah, for this case, x, the independent variable. Then what happened to the function y? If you are given in terms of times, then the function might be position vector, might be acceleration or velocity. Could be anything. Okay. The basic idea is that we want to find given how much change in x, very small change. That x means very small change. Then what happened to y? How big or how small y change? All right. If you look at this, if you compare with this kind of function, for example, this kind of function, all right, compare these two. So obviously in this case, given small delta x, you can see pretty big difference in y as compared to this one. Okay, given small delta x, you can find delta y, but the size is compared with that, this is much smaller than that. Okay, so that's a basic idea of rate of change. Now in the case of directional derivative, so normally what we say, we want to find we want to estimate. You have to estimate the rate of change. I just put it ROC, rate of change of f in the direction of u, in the direction of u. Remember that u is a unit vector. U is a unit vector, and of course we need a point. Let's say at point P naught. Yeah, point P naught means we have a specific points. You can see in the note that we have df dt at point P naught. This is del f P naught at point P naught u. If you look at this part here, this is the directional derivative of function f in the direction of u at point P naught. So if you want to estimate the rate of change, this is the focus now. Estimate the rate of change of f. So what we need, rate of change means is involve time. So in this case, I can, if you consider this as a normal division, so what we have, df is, we have this at point P naught dot u. Alright, and those dt I can put there. That. Okay, so this is the increment for t. That one you can find given the increment in t. This is given. then definitely we can find the rate of change for the function. Okay, only that. So in this case, you have to, in this subchapter, you have two case that you need to consider. First thing is find the directional derivative for the function f in the direction of u at point P naught, and another one is rate of change. Okay, for the exercise example, I think you can refer to our notes, to the previous video that I have recorded. Now that's all about the directional derivative. Now the second part in this video, I would like to talk on equation of tangent plane. Right, now equation of a tangent plane. What is the equation of tangent plane? Equation of tangent plane. Now you have equation, you know what equation is. You have tangent, you know what tangent is, and you have plane, you know what plane is. If you put it together there, okay, tangent plane, which means a plane that touch to a certain point to a surface. So in this case, we need a surface. So I have, let's say I have this surface. Okay, let's say this is my surface S. Okay, and then you have a tangent plane. What is tangent plane? Tangent plane is that we have a plane. Okay, this plane touch. Okay, this plane touches the surface S at one point only. At one point only. Let's say this point is P naught. You can have this P naught, X naught, Y naught, Z naught. So this is the equation, this is the plane that we are looking for. Alright, this is the plane that we are looking for. This is, let's call this plane M. Okay, ada gangguan. Aduhai. Alright, so where am I? Okay, so forget about whatever sound that you might hear, then just forget it. Just focus on this video. Okay. Okay. All right. Now let me go to the basic one. First thing, in the plane, for the equation of plane, we know that for the equation of plane, how to find the, for the plane, how to find the equation of the plane? What do we need? We need a point. All right. We need a point. What else do we need? We need a normal to the plane. Normal to the plane. This compulsory, when you find the equation, when we want to find the equation of a plane, these two items is compulsory. You must have this. If you don't have this, then you cannot find that. So you need to find normal. You need to have the point on the plane. For the tangent plane, we have the same concept here. But how to find the normal to the plane? Now, this is our surface given by S. So this surface, let's call that F, Sx, Y, Fy, Fxy, Z. You might have two variable function. You may have three variable function. Okay. How to find normal to the surface? Normal to the surface is given by del F. Okay, you apply this del F. That del F give the direction normal to the surface. Remember that, normal to the surface. There, in that direction, here you may have this direction. Okay, all this del. You might have this direction, all this del. Okay, so in order to determine this direction, we need all this point. We need all this point. If I have this P point P1, if I have this P point P2, if I have this point P3, then I evaluate those at point P1, then it will give direction. It will give the direction at point P1, give the direction at point P1, that this direction normal to the surface. For at point P2, this is normal to the surface. At point P3, this is normal to the surface. Which means, if you want to find direction that normal to the plane, to the tangent plane, so we need to find that, because this P naught on S, this P naught on M. Okay, P naught on S, P naught on M. And then if you find the del F, so we have this direction tangent to the surface, which also tangent to the plane. So we have this. Understand? So I think that's very clear. That's so in order to find that equation of the plane, tangent plane, we can find the normal. We have a point. So that's enough for us to find the equation for the plane. Now, another one is we might want to know is the normal line. Normal line means, normal line. Normal line. Equation of normal line. What is the equation of normal line? Equation of normal line here means we want to find the equation of a line that perpendicular to the tangent plane. So let's say we have this normal line that perpendicular to the tangent plane. You know how to find the equation of equation of a line. How? We need a vector that parallel to the line. Let's call that line L. Okay. We need a point on L. A point on L, you can choose that given point. Okay. Now, having these two, you need the vector, you need a point, you can find the normal line. So V in this case, V which is parallel to L, this is del F at P naught. Yeah, because this del F at point P naught will give you a vector that normal to the plane, which means it's parallel to the line that normal to the plane. Okay, so I hope you can understand that. I don't want to give, or do I need to give an example? I think okay, I give you an example. Let's say I just pick up any function. Okay, I just pick up any function. So let's consider we have a function. Consider this function. This is a surface. Right? So let's say we have 3x squared plus y squared plus z squared. Let's say that function. Okay, and so this function, this function is this surface. This is just surface f x y z, which is this. We need a point on the surface. So I don't know. So let's say this function passing through the origin 0, 0. Okay, so let's say we have at point 0, 0, 0. So let's say I have this point. Okay, so we need to find normal equation of tangent plane at that point for that function, for that surface. Okay, so first thing is you need to find del f. Del f in this case is, so we have del x 6x, del y you have 2y, del z you have 2z. Okay, so this at those 0, 0, 0, f at point 0, 0, 0, that you have 0, 0, 0. Where is the direction of 0, 0, 0? I have explained to you what is the direction of 0, 0, 0. Okay. What else? So you have a point. You want to find the equation. So that's all. So we have that vector. So we have x minus x naught, right? Times normal. This is normal. So you got 0 plus y minus y naught, 0 plus z minus z naught. You got 0 times 0. You got 0 equal to 0. So you can see in this case 0 is equal to 0. It is fair. But of course, I think I chose the wrong point, so that's why we have this kind of thing. That's on the right side. On the left side, you got 0, which is not quite accurate. But in terms of calculation, this is true. Okay, in terms of calculation, this is true. So what I want to show you here is the process how to find the equation of tangent plane to the surface. Equation of plane to the surface. Okay, you can choose other point. For example, f z equal to f. Let's consider two variable function. Let's say 3x squared plus y squared at 0.11. So at I can choose 1, 1. So 3, 4, 4. Okay, at that point. So this is correct. So you will not get 0 in this case. Okay, you will not get 0 in this case. So you can try this. Del f that give you 6x 2y. So at point P, let's go, this is point P. Okay, at point P. So what is this? You have 6. Right. So you have 2. See, you know 0. Now you can proceed the rest. Okay. For the equation of this is the equation of tangent plane. Equation of tangent plane. So you have x minus x naught times a, which is 6. Your x naught you can choose. This is 1 at this point, plus y minus y naught. Your y naught is 1, and that normal, so this is 2, this is equal to 0. So you can find the equation x minus 1. So you have 6x minus 6 plus 2y minus 2 that give you 0. So yeah, you can proceed the rest. Okay, so and then if you want to find the equation of normal line, equation of normal line, what we need v, we need p naught. That's all. Our v is del f at point P. Okay, then you can use x is equal to x naught plus tv1, y equal to y naught plus tv2, z equal to z naught plus tv3. This is the equation of tangent line. What is v1, v2, v3? v1, v2, v3 is del f, which is this. Okay, what is x naught, y naught, z naught? You can choose any point on the line. So in this case we choose at point P, so you can use that. Alright, so that's all. Should have no problem. Alright, so I stop there. Thank you.